Okay, so while I'm waiting for this to appear, maybe it won't, I'm going to ask everybody if they would let's try this again. Please hop into your DeLoreans, go 88 miles per hour, and travel back to Monday afternoon when we were having a discussion following Mike Lamone's first of 38 talks about the nature of outflow that was manifesting in global models where the inner boundary conditions were a uniform density and zero radial velocity. And we have a manuscript and review on this, so I wanted to quickly comment. This plot up here is a very quick summary of what's going on in terms of net fluence here in green. So if you take a shell just outside the MHD boundary and calculate the particles, the plasma passing through it, you get a net fluence, particles per second, that hovers right around that magic number again, 10 to the 26th. Additionally, even though your inner boundary conditions are static, you see that this fluence is not. For northward IMF, or between northward to southward IMF, you see a sudden jump in the total fluence just outside the inner boundary. Further, if you investigate the flux passing through that little test shell, you see that for northward IMF, you see upward fluence about the polar cap. It's kind of washed out on the projector, but a little bit of cusp upward flux. I keep interchanging those words, I apologize. This is flux, this is fluence. The sun is over here on these diagrams. For the southward IMF, not only is the overall magnitude increased, but the location of the flux has moved to lower latitudes, looking more like it's following the field-aligned currents, and the dayside cusp area flux has increased as well. Now, I like to borrow a term from American law and refer to this as de facto outflow. That is, in practice, but not necessarily ordained by law. All of this is arising not because we are enforcing it by applying some special boundary conditions from an empirical or first principles-based model, but it comes from a set of simple boundary conditions that the early MHD developers picked because they wanted their code to be stable. And this is just a somewhat surprising side effect of that. Now, I don't want to spend too much time on this because this is not the focus of my talk, but what we found was that the macro level patterns that you see in observations seem to reflect quite clearly in the MHD code. So this is cross-polar cap potential when we change the IMF from northward to southward in a step function, and the net fluence coming from the inner boundary follows that with a correlation coefficient of nearly 1. And if you do a similar study where you change the dynamic pressure of the solar wind, over time you see that the fluence arising from the noon-centered quadrant near the inner boundary follows that impulsively. And so these are things that have been published using observations, and for various reasons they're reflected in the code when you have these very simple boundary conditions. Okay, so now we're going to get back in our time machine and go back to the future, which is what I want to talk about. We've been doing a lot of work at Michigan to advance our codes so we can better study the mass coupling relationship between the ionosphere and the magnetosphere. And there are two I want to talk about today. The first is introducing an alternative code to prescribe outflow in BATS-RS, and that is the Utah State Generalized Polar Wind Model. And the second advancement is expanding our two-fluid version of BATS-RS to 3 fluids so that we can unambiguously investigate the effects of ionospheric oxygen and hydrogen on the magnetosphere in contrast to solar wind hydrogen. I have quite a few collaborators on this. The Michigan team, of course, Vanya Jordanova from Los Alamos, Alex Glosser from NASA Goddard, the various Utah State gang, and Rick Chappell. So over the past decade or so, global models have really played a critical role in helping us understand the extent to which the ionosphere mass affects the magnetosphere. And there's going to be some more talks on this afternoon, but it's really varied from changing the size and shape of the magnetosphere to affecting the formation of the plasma sheet and the ring current, and potentially even being one of the causes or drivers for global sawtooth oscillations. However, I would strongly assert that the details of this coupling remain a mystery to us. We really don't understand it very deeply. And let me show you a couple of figures that I think illustrate that. This is a figure from my 2011 paper where we're looking at the plasma sheet conditions at geosynchronous, ranging from dawn, midnight to dusk as you move vertically, throughout a storm as you move horizontally, in terms of number density, percent oxygen by number, and temperature. And this figure was extracted from an MHD simulation where we had the polar wind outflow providing outflow to the code. Now what you see here is that there is a lot of structure, not only in time, but also in space. And what we found in this paper was that this structure then affected the ring current development. So all of these little details were important. On the right, we see the DeMars and Shunk picture that Bob showed this morning, the campfire flame. And again, this is a log oxygen density. You see a lot of detail and structure. Now, something that I don't think we have a very good handle on at all is how all of this detail is, or maybe even is not, a function of all the things going on here. And if we're going to address this properly, we need to continue to improve not only our outflow codes, but our codes that are transporting that outflow to the regions of interest. So this is the simulation setup that, one of the simulation setups that we use at Michigan, but I want everybody to kind of squint your eyes and let all these arrows and details go blurry. And if you do that, you see the general approach that many different groups take in the community. You essentially start with some way to drive outflow, whether it's an empirical model, a simple constant, or a numerical model. And typically at Michigan, we use Alex Glosser's polar wind outflow model. You then have some sort of global model to transport and let the ionospheric mass as well as solar wind mass evolve. We're using, of course, BATS RSMHD. And then if you're feeling a little more adventurous, you may include a model of the ring current to better capture the intermagnetosphere dynamics. And for the studies that I'm working on, I use Los Alamos' RAM-SCB. At Michigan, we use the space weather modeling framework that allows us to execute, synchronize, and couple all these models together. But there are many different approaches you can take here. Now, for the science questions I just laid out, we really want to address two areas. One, the delivery of ionospheric mass to the magnetosphere, and two, ensuring that we are getting the most important physics, or the most relevant physics, as we transport that mass through the magnetosphere system. So let's start by talking about number one. We have recently introduced a new model, recently coupled a new model to BATS-RS, and that is Utah State's GPW model. Now, Bob already has waxed poetic about it, so I won't carry on. However, I do want to point out that it captures far more non-classical acceleration mechanisms, such as collisional effects, wave-particle effects, etc., that the version of the PWAM we use does not currently have. So installing a new code like this allows for some interesting comparisons. The first one is that we can hold our transportation method, BATS RSMHD, that physics part, constant, and change how we are setting the ionospheric outflow to see how the global magnetosphere responds to a different mass driver. The other thing we can do is that if you have a lot of people using the same model, we can hold the mass input into the magnetosphere constant and see how the effects depend on your transportation mechanism, whether it's subtle differences between different applications of an MHD code or something more fundamental like coupling the GPW to a large-scale kinetic model. This is really the goal of our GEM focus group, the outflow merging modeling and measuring, and so we're really hoping to get a lot of people contributing to this effort. Oh, before I go on to the results, I do want to talk, where we stand now with this is that the GPW is great. You could consider it to be the Cadillac of outflow models that are currently in use. However, it comes at a cost, a very high computational cost. So for a first level proof of concept simulation, we are taking results from an already performed simulation and applying a one-way coupling. And so this is what that looks like. So what we're looking at here is the results for the GPW, and these are the hydrogen and oxygen fluxes driving BATS-RS, and now we're looking at the noon midnight meridian plane in terms of the logarithm of percent oxygen by number, so the darker greens are tens of percent, for a very simple idealized solar storm. We're going from a weakly northward IMF configuration to a strong southward, negative 10 nanotesla, for 2 hours, and then returning northward again with an associated pressure pulse. This is the resulting DST curve calculated via Biot-Savart integral from BATS-RS, and here we do not have any intermagnetosphere code coupling. It's just the MHD. So I'm going to go ahead and let this guy run, maybe. Oh, PowerPoint, you fight so hard. Now, there's not a whole lot interesting here yet, but one of the things that stands out to me is that you see these little bursts of flux coming up, and you probably missed it, but if you look carefully towards the inner boundary, you will see those mapped to the MHD domain. So already we're starting to see some of those details pass from code to code, and for me that's pretty exciting. To get an idea of how this differs from our previous approaches, we can look at DST. So for the default MHD setup, our DST turns northward with a storm sudden impulse, and then because this de facto outflow method does not have oxygen, it is increasing the amount of particles, but it's really a weak mass coupling. We're not spitting out anything heavy. And so the DST is dominated by the Chapman-Ferraro current increase that you get by compressing the magnetosphere. So it turns northward, stays northward, and then relaxes down once you leave the IMF-BZ negative window. If you turn on the PWAM, which is what you get with the purple code, or the purple line, excuse me, you do see the storm sudden commencement. The mass buildup helps build a stronger ring current and plasma sheet, but it's very gradual and then relaxes to a new equilibria. And I think if you were cataloging storms via DST, you wouldn't consider this to be a very major one. With the GPW, however, during the main phase, the additional mass drives the DST to negative 80, and then once IMF turns northward again, we have a quick and then a slower recovery. And so that's very interesting. Already with this simple proof of concept run, we're seeing some big differences. And those differences are really manifesting because of the amount of flux that you're getting from the GPW versus PWAM. So this is the number density in terms of oxygen for PWAM and GPW. In a very simple qualitative manner, yeah, they do look very similar. The patterns tend to follow where you'd expect the field line currents to be, but the scales are different by a factor of 2. So there's more oxygen available, and further, the velocity at which that's the mass it has as it's being handed to BATS-RS is far greater for GPW. So for PWAM, we're looking at a maximum of 5 kilometers per second. For the GPW, it's in the order of 20. And so the amount of flux entering the global model is far higher. So now I want to move on from that and talk about improving the transport. In the real magnetosphere, we know there are at least 3 distinct populations: the solar wind hydrogen, the ionosphere hydrogen, and the ionosphere oxygen. We also know that they are going to enter the magnetosphere at different locations with different characteristics and evolve independently. One example of that is the geomagnetic mass spectrometer effect, where 2 particles of the same energy, the lighter of one, say the ionospheric hydrogen, is going to be able to go much further down tail than its fat, slow brother oxygen. And when they hit the plasma sheet, if you think in very simple terms, they begin to adiabatically heat as they advect inwards. The one that makes it further down tail is going to experience much more adiabatic heating than the one that makes it lands nearer to Earth. So if you only have a 2-fluid approach, you're going to miss some of these dynamics. And here are a couple of examples from our own work. Let's suppose that you don't separate out the ionosphere and the solar wind populations. In the cusp, you have upflowing ionosphere plasma and downflowing solar wind plasma. And if you have one momentum equation between the two, they stop. They reach an equilibrium and they stop. And this is pretty catastrophic if you're trying to figure out what your outflow is doing, because it's reflected back down the cusp and then acts as if it were entering like a solar wind population. And so this is a pattern I see a lot of, and I was not happy with it. Let's suppose that you don't separate out oxygen and hydrogen in your plasma sheet. And this is a problem when you're coupling to a ring current model. Now, typically what you do is that, okay, we have a temperature and a density for a population. We assume some distribution about that, usually a Maxwellian, and then we hand it to the drift model. Now, if you have one temperature between your oxygen and your hydrogen, those two are going to advect through the ring current in the exact same manner. And so these are RAM-SEB results where that happened. This is the energy spectra for hydrogen and oxygen. And once the storm starts, they look like scaled images of each other, which again is not very realistic. As such, we've expanded our 2-fluid version of BATS-RS to 3 fluids. And so our picture now has more arrows. I apologize for that, but more arrows are good sometimes. So I want to show you again another proof of concept study where we're going to keep it very simple. We're going to turn off the polar wind outflow model and turn off feedback from the ring current to BATS-RS and see if just by separating out these 3 populations, if it really makes a difference to the plasma sheet and the ring current. How much time do I have left? 2-minute warning. Look at that. All right. So I'm going to go ahead and skip some of the details. But again, it's another very idealized simulation. Northward IMF for 5 hours, southward IMF for 5 hours. And let's start by looking at the flow paths taken by populations starting over the poles. For a single fluid plasma, the population we picked didn't start from there. It actually originated even pre-cusp a little bit. So that is, that problem area I pointed out before. But once we separate out our ionospheric populations from our solar wind populations, this problem no longer manifests. Additionally, and what was very exciting for me once I did this first simulation, right away we see that the geomagnetic mass spectrometer effect is taking hold. This particular hydrogen fluid parcel was able to escape down tail, while this particular oxygen parcel was captured and advected earthward. So down here we're looking at the temperature, total velocity, and number density along the streamlines I'm showing here. For each population, they experience a huge energy boost as they pass into the central plasma sheet near the reconnection region. This is on a log scale. And then we start to see the smooth adiabatic increase in temperature. And even though our oxygen started off with a higher temperature towards the inner boundary, it receives a little less of an adiabatic kick than in our single fluid case. And that's not exactly an apples-to-apples comparison because they're different simulations. But right here we're seeing what we'd expect to see, which is very exciting. To look at the bulk plasma sheet parameters, I'm going to go back to the type of plot that I showed you on my second slide. So we're looking at number density and temperature for solar wind hydrogen, ionosphere hydrogen, and ionospheric oxygen. Again, dawn, midnight to dusk across here, our southward turning happens at the dashed line. Pre-storm, this resembles what Mike Lamone was talking about in his second of 352 talks, or first of 352 talks. We have a cold, dense, solar wind dominated plasma sheet. When we turn southward, this mass is compressed up against geosynchronous, or through geosynchronous, and you can see the contour starts to warm up into the kilovolt range in terms of temperature. And we're seeing about 10 particles per cubic centimeter here. But this population quickly washes out and is replaced by a tenuous hot population. This is the solar wind. 2 minutes. That was my 2-minute warning. Okay, brilliant. I'm doing great then. This is the population of the solar wind that is entering over the cusp in a typical Dungy-style fashion. There's not a lot of it, but it's there. Before the southward turning, we didn't have a lot of ionospheric mass. It does increase after the southward turning, and it warms up. So we're seeing different densities and temperatures for each. Now the last thing I want to show you is taking those properties and mapping them into the ring current model. So what we're going to do is we are going to assume a Maxwellian about the density and temperature for each population. Now, RAM-SCB only has one bin for hydrogen at each energy, so we're going to take two Maxwellians, one for solar wind and one for hydrogen, and sum them together. Okay, so what we're looking at here, the solid lines on both of these plots are hydrogen, the dashed lines are oxygen. We're looking at midnight in dark blue, dawn in kind of gold, and dusk in purple. This is right after the southward turning, so this is the cold, dense plasma sheet warmed up a little bit as it begins to vect earthwards, and we have a tenuous and not terribly warm yet oxygen population that's just starting to reach the geosynchronous point. Over here, what we're looking at is looking down at the Earth, the pressure distribution in RAM from hydrogen and oxygen, or just as the storm's starting. It looks very similar. And we can quantify that by taking radial slices. So this is L versus... I'll finish the slide quite quickly. Wow, that thing really freaks out when you're taking too much time. No, that's fine. I'm surprised it wasn't my phone. Energy density versus L shell, so we can kind of quantify the differences here. As the storm continues, we start to see the contribution from all three populations, the warmer oxygen, the hot but tenuous solar wind, and the cooler and denser ionosphere hydrogen. And I'm just going to flip through these real quick. As the storm continues, we start to see two distinct ring currents. A hydrogen one, which for this run was colder, and so E cross B drifts deep into the inner magnetosphere and gives us a nice sharp pressure peak, versus a broader oxygen ring current. It was warmer at the outset, so it gives us a nice broad distribution across many L shells. And so I was very excited to see this result. By adding this additional fluid, we were able to see a lot more interesting effects throughout the plasma sheet and inner magnetosphere. I'm out of time, so I'll leave this on the screen. The one point I would like to make on the way out is that when you turn on mass coupling from the ionosphere to the magnetosphere, especially causally driven mass coupling, the magnetosphere-ionosphere system becomes an even more tightly coupled and nonlinear system than when you only include ionospheric electrodynamics. And I think it's a very exciting thing to look at. Thank you.
Thank you very much. That was, of course, very interesting to me personally. We have time for a few questions. Let's see. In the back.
Hi. Dan, you showed a plot where you had green on green O plus percentage early on in the talk. Green getting greener. There we go. Your entire magnetosphere filled up very quickly with oxygen ions, if I can read the green scale.
Sure.
And they persisted for a very, very long time, even after the outflow seemed to diminish. How do you account for that long lifetime of O plus in your system? That's my first question. I mean,
Sure.
Your O plus is almost, there's almost nothing coming out, if I can read that correctly. And then,
Oh, here?
Yeah.
There's stuff. It's a poorly chosen scale, I think, on my behalf.
But look, I mean, for 10, 15 hours after that, you still have O plus in your system.
Yeah, so I would say two things. One, this is a log scale. So we're probably sitting, for some of these colors, we're sitting below 10%. So that's a little misleading. I was really trying to, I had this movie earlier, and if you didn't do it a log scale, it was hard to see much happening, and if you turned on the log scale, it was easy to see, what you said. I would say also here we're still looking at, in terms of oxygen outflow, on the order of 10 to the 7th particles per cubic centimeter per second. So there still is oxygen outflow there.
Okay.
Yeah.
My comment I have also about your later results is that you invoked adiabatic drifts for O plus and H plus to make some conclusions, and especially in the case of O plus, that's not necessarily a correct statement. In the tail, you may get O plus hitting closer to the Earth, but O plus is also non-adiabatic, much, much closer to
Yeah.
the Earth than H plus is.
So I think that's a really important point, and I was expecting that comment from either you or Lynn based on her comment earlier this week. And I think that's absolutely true, that with oxygen's gyro radius, the adiabatic assumption kind of goes out the window quite quickly. However, I think it's still important to separate these out. There are a couple of ways you could think about this, right? You could address this in a more self-consistent manner by doing some sort of, particle and cell approach, or, your large-scale kinetic model really is excellent at capturing some of these, but you have limitations there too. And so I think the improvements we get from the 3-fluid multi-fluid are important. They're not entirely accurate, but they're important, and I think they're a stepping stone to what Alex said, which is, okay, 3-fluid plus anisotropic, 3-fluid plus coupled to a particle tracer or a PIC code, because separating out these fluids does give you different pressure distributions inside the MHD and changes the magnetic field self-consistently. So it's always a trade-off, but you're right. Yes.
I may have misunderstood, but I think it's your second slide. I mean, it is a very simple-minded Fortran for 1974 comment. You said, I thought you said, that all that flame on the left, you didn't know how much of it is due to the flame on the right. Now, I would say, why don't you run a simple non-flaming right and see what the left looks like? I may be being too 1974 thinking here.
So there are studies that show this, and I know Roger's going to highlight some where basically you're doing controlled experiments at Twin U. I'm familiar with her work, of course, working with Aaron Ridley, and Mike Wiltberger has done some of this. You have a good point, but a lot of times the best controlled experiments go haywire. Those results really go out the window when you try to do real-world simulations, because things are changing so much faster and with different time scales and different spatial distributions. I think Vanya Jordanova and I have a bunch of these results from idealized runs, and you never see this much structure until you really let the solar wind oscillate and turn on all the bells and whistles. I think it's a fair statement, though. Okay. Thank you guys very much.
Question. May I ask?
Sorry.
Dan, would you go to the slides toward the end where you had the 3 fluids, and I just wanted to see what the contribution was from the ionospheric hydrogen point of view.
Here?
You had those, I think you had the curves in there, let's see, toward the end. Just want to make sure I understand the
Was it
ionospheric
this one?
Yeah.
Okay.
Yeah. So the stuff that started at low energy out of the ionosphere.
Yeah, so this is... So what part do you specifically have a question about, or just in general?
Just the relative strength of the ionospheric H plus versus
The solar wind.
H plus.
Sure. Okay, let me get my laser pointer out here again. So just after the southward turning, I'm going to go here because it's very easy to explain here. You have the very dense pre-existing solar wind plasma sheet that is energized as it moves earthward because your convection is now earthward. And for this first static picture here, that is this bump, and your ionospheric contribution is cold and not quite there. When we move forward deeper into the storm, the solar wind that you're getting in the central plasma sheet is hotter, but very tenuous. And so we're on a log scale here. And over here, we're seeing the cooler ionospheric hydrogen from this particular run. Now, the way this curve has arranged itself is very specific to this idealized storm, and it could be very different if we did something, different. Okay.